Synchronous machines are principally used as alternating current or AC generators. They supply electric power used by all sectors of modern society: industrial, commercial, agricultural, and domestic. Synchronous generators usually operate together or in parallel, forming large power systems supplying electrical energy to loads and consumers. They are usually found as large units, their ratings ranging from tens to hundreds of megawatts that convert mechanical power to AC electric power. The source of mechanical power, the prime mover, may be diesel engine, a steam turbine, or a water turbine, or any similar device. For high-speed machines, the prime movers are usually steam turbines employed by fossil or nuclear energy resources. Low-speed machines are often driven by hydro turbines that employ water power for generation. Smaller synchronous machines are sometimes used for private generation or as standby units with diesel engines or gas turbines as their prime mover. In a synchronous generator, the rotor magnetic field is produced either by a permanent magnet or by applying DC current to a rotor winding to create an electromagnet. The rotor of the generator is then turned by the prime mover, producing a rotating magnetic field within the machine. This rotating magnetic field induces a three-phase set of voltages within the stator windings of the generator. Two terms commonly used to describe the windings on a machine are the field windings and the armature windings. In general, the term field windings applies to windings that produce the main magnetic field in the machine, and the term armature windings applies to the windings where the main voltage is induced. For synchronous machines, the field windings are on the rotor, so the term rotor windings and field windings are used interchangeably. Similarly, the terms stator windings and armature windings are used interchangeably. The rotor of a synchronous generator is essentially a large electromagnet. The magnetic poles on the rotor can be either salient or non-salient. The term salient means protruding or sticking out, as shown here. A non-salient pole rotor looks something like this. Note that the windings of the electromagnet are embedded in notches on the surface of the rotor, like this two-pole example. Non-salient pole rotors are normally used for 2 and 4-pole rotors, while salient pole rotors are normally used for rotors with 4 or more poles. In salient pole machines, when 4 or more poles are on the rotor, the multi-pole machine will look something like this. The magnetic fields are generated by DC current flowing through the coils on the protuberances on the rotor. They are wound alternately, creating a north and south pole on each of the protuberances. It is the flux in the air gap that we are concerned with, so I will remove the innermost designation. Not that it's not there, it's just that we want to concentrate on the flux that is in the air gap. An 8-pole rotor would look something like this. Again, notice the alternating north and south poles as you go around the rotor faces. Salient pole rotors are usually of large diameter and shorter length. They are typically used in lower speed electrical machines, say 100 RPM to 1500 RPM. These salient pole rotors allow for better ventilation. The pole faces are so shaped that the radial air gap length increases from the pole center to the pole tips, so the flux distribution in the air gap is sinusoidal in shape, which will help the machine generate sinusoidal outputs. In some cases, slip rings and carbon brushes are used to connect the DC supply to the rotating field. Slip rings are metal rings completely encircling the shaft of a machine but insulated from it. One end of the DC rotor winding is tied to each of the two slip rings on the shaft of the synchronous machine, and a stationary brush resides on each slip ring. A brush is a block of graphite-like carbon compound that conducts electricity freely but has very low friction so that it doesn't wear down on wear the slip ring out. If the positive end of the DC voltage source is connected to one brush and the negative end is connected to the other, then the same DC voltage will be applied to the field winding at all times, regardless of the angular position or the speed of the rotor. Slip rings and brushes create a few problems when they are used to supply DC power to a field winding of a synchronous machine. They increase the amount of maintenance required on the machine, since the brushes must be checked for wear regularly. In addition, brush voltages drop can be caused by significant power losses on the machine with larger field currents. Despite these problems, slip rings and brushes are used on smaller synchronous machines because no other method of supplying the DC field current is cost effective. On larger generators and motors, brushless exciters are used to supply the DC field current to the machine. A brushless exciter is a small AC generator with its field circuit mounted on the stator and its armature circuit mounted on the rotor shaft. The three-phase output of the exciter generator is rectified to direct current by a three-phase rectifier mounted on the shaft of the generator, and it is then fed to the main DC field circuit. By controlling the small DC field current of the exciter generator located on the stator, it is possible to adjust the field current on the main machine without slip rings or brushes. Since no mechanical contacts ever occur between the rotor and the stator, a brushless exciter requires much less maintenance than slip rings and brushes. To make the excitation of a generator completely independent of any external power sources, a small pilot exciter is often included in the system. A pilot exciter is a small AC generator with permanent magnets mounted on the rotor shaft and a three-phase winding on the stator. It produces power for the field circuit of the exciter, which in turn controls the field circuit of the main machine. If a pilot exciter is included on the generator shaft, there is no external electric power required to run the generator. Many synchronous generators that include brushless exciters also have slip rings and brushes so that an auxiliary source of DC current is available in case of emergencies. Synchronous generators are, by definition, synchronous, meaning that the electrical frequency produced is locked in or synchronized with the mechanical rate of rotation of the generator. A synchronous generator's rotor consists of an electromagnet to which direct current is supplied. The rotor's magnetic field points in whatever direction the rotor is turning. Now, the rate of rotation of the magnetic field in the machine is related to the stator electrical frequency by the equation FSE is equal to NMP all over 120, where FSE is the electrical frequency in hertz, Nm is equal to the mechanical speed of the magnetic field in revs per minute, or rotor speed, and P is the number of rotor poles. Since the rotor turns at the same speed as the magnetic field, this equation relates to the speed of the rotor rotation to the resulting electrical frequency. Electrical power is generated at 50 or 60 hertz, depending on where you are. So the generator must turn at a fixed speed depending on the number of poles on the machine. For example, to generate 60 hertz power in a two-pole machine, the rotor must turn at 3600 RPM. To generate 50 hertz power in a four-pole machine, the rotor must turn at 1500 RPM. The required rate of rotation for a given frequency can always be calculated from the above formula. In synchronous generators, a magnetic field emanates from the north pole of the rotor through the air gap into the stator, traveling through the metal stator laminations and re-enters through the south pole air gap back into the rotor. This includes non-salient pole type rotors and stators that have their windings distributed in slots around the circumference of the machine. As the rotor rotates, the magnetic field travels with it, linking the various stator windings as it travels. The magnetic flux in the air gap as the rotor travels links different stator coils at different times depending on the position of the rotor. The flux density across the face of the pole on the rotor will depend on various elements, but it is designed in such a way as to be sinusoidal across the face of the rotor. In actual fact, I have compressed the wave shape here in the air gap in order to show you its sinusoidal shape. In actual fact, it looks more like this. The machine will have one complete cycle of magnetic flux wave for every two poles of the rotor. In order to study this generator further, I'm going to remove the bulk of the stator frame detail. Just as a three-phase set of currents in a stator can produce a rotating magnetic field can produce a three-phase set of voltages in the coils of a stator. The equations governing the induced voltages in a three-phase stator will now be developed. To make the development easier, we will begin by looking at just one single-turn coil. Then we'll expand the results to a more general three-phase stator. I'm moving that coil off to the side so we can have a clear look at it and its dimensions. This slide shows a rotating rotor with an angular velocity of omega having a sinusoidal distributed magnetic field in the center of the stationary coil. Notice that this is the reverse of the situation previously studied, which involved a stationary magnetic field and a rotating loop. In this case, the wire is stationary and the magnetic field is moving. However, the relative velocity between the stator coil and the magnetic field or magnetic flux density is the same. Vector B is the flux density in the air gap between the rotor and the stator. It varies, as I said, sinusoidally with magnetic angle alpha of the rotor, while the direction of B is always radial to the rotor. That is, it's 90 degrees to the rotor. Note that at some locations around the air gap, the flux density vector will be pointing out from the rotor, from the North Pole, and some will be pointing in towards the rotor, the South Pole. This sort of flux distribution is the ideal to which machine designers aspire. If alpha is the angle measured from the direction of the peak rotor flux density, B subscript M, then the magnitude of the flux density vector B at any point around the rotor is given by this equation. B is equal to B subscript M, the maximum flux density, times cosine of alpha, which will be negative for alpha greater than 180 degrees. The flux density vector pointed in towards the rotor. The equation for the induced voltage in the wire, as we have seen before, is given by this equation. E is equal to V cross B times L, where V is the velocity of the wire, B is the magnetic flux density, and L is the length of the conductor. The voltage induced in the coil, which we'll call E subscript IND, will be the sum of the voltages induced in each of its four sides: EBA, ECD, EDC, and EAD. For segment AB, assuming that B is directed radially into the rotor, the angle between V and B in this segment is 90 degrees, while the quantity V cross B is in the direction of L. So, E subscript AB that equals V cross B dot L is just going to be the magnitude of V times the magnitude of B times the magnitude of L, directed into the page for alpha less than 90 degrees. This is by the right-hand rule. That is, A is positive with respect to B. This means the voltage vector is the same direction as the segment AB, meaning the voltage rises from B to A. Therefore, the induced voltage on this segment of the wire is VBL from B to A. The voltage on segments BC and DA is 0 since the vector quantity V cross B is perpendicular to L. So E subscript BC, which is equal to V cross B dot L, is equal to 0, is equal to E subscript DA. Now for segment CD, assuming that B is directed radially out from the rotor to an angle between V and B in segment CD, and it is 90 degrees, while the quantity V cross B is in the direction of L, so the voltage E subscript CD, given by the equation V cross B dot L is just the magnitude of V times the magnitude of B times the magnitude of L directed out of the page. This means the voltage vector is the same direction as the segment CD, meaning the voltage rises from C to D. Therefore, the induced voltage on this segment of the wire is VBL from C to D, which ultimately now means the total induced voltage is made up of the voltage across segments BA and DC only. This means the total induced voltage is 2 times V times B times L. Since the relative angular velocity of rotation is omega radians per second, then alpha will be omega times t, where t is equal to seconds. And it is also noted here that it is the relative angular velocity we're talking about in radians per second. Therefore, B equal to Bm cos alpha can be rewritten as B is equal to Bm cos omega t. Keep in mind that B is a varying magnetic flux as we go around the air gap, and Bm is the maximum value of that varying magnetic flux. This means the induced voltage in the coil is varying, or is a varying value, and is given by the equation. The E induced is equal to 2 times V Bm L cos omega t. Since the tangential velocity of the ends of the conductor are given by the equation V is equal to R omega, where R is the radius of the diameter of the rotor, the flux passing through the coil can be expressed in terms of phi, which is equal to 2 times the radius of the rotor times the length of the L, the length of the coil, times the Bm. We can rewrite the equation as, using these two equations, we can rewrite the equation for the induced EMF. E induced is equal to phi omega cos omega t. It is important to remember that omega is the relative angular velocity, meaning that it is the difference between the coil speed, which is 0, and the speed of the magnetic field as it moves past the conductor coils. While this equation describes the voltage induced in a single turn coil, if the coil in the stator has N subscript C or NC turns of wire, then the total induced voltage of the coil would be given by this equation, which introduces the number of turns into the equation as well. Notice that the voltage produced in the stator of this simple AC machine winding is sinusoidal, with an amplitude which depends on the flux phi in the machine, the angular velocity omega of the rotor, and a constant depending on the construction of the machine, NC, or the number of turns in this case. This is the same as the result that we obtain for a simple rotating loop in a magnetic field. Note that the equation contains the term cos omega t instead of sine omega t found in some of the other equations that we used. The cos term is of no special significance compared to the sine term. It is resulted from our choice of reference direction for the angle alpha in this derivation. If the reference direction for alpha had been rotated by 90 degrees, we would be dealing with the term sine omega t instead. If three coils, each of NC turns, are placed in the stator equally spaced at 120 degrees around the rotor as shown in this slide, then the voltages induced in each of them will be the same in magnitude but will differ in phase by 120 degrees. The resulting voltages in each of the three coils are, for the orange coil, we'll designate it as EAA primed as a function of t is equal to NC phi omega cos omega t. The green voltage given by E subscript BB primed as a function of t is equal to NC phi omega cos omega t minus 120 degrees. And the third coil, colored black in this case, would be given by E subscript C primed as a function of t is equal to NC phi omega cos omega t minus 240 degrees. Therefore, a rotating magnetic field can generate a three-phase set of voltages in such a stator. The peak voltage in any phase of a three-phase stator of this sort is given by E subscript max, or E max, is equal to NC phi omega. Remember that omega is the relative angular velocity. While this equation describes the voltage induced in a single turn coil, since omega is equal to 2 pi f, this equation can also be written as the magnitude E max is equal to 2 NC phi pi f, where f is the frequency which the magnetic field is passing the coils in the circuit in cycles per second. If the magnetic field goes through one cycle in the air gap over the circumference of the rotor, F will also be the speed of the rotor in cycles per second. This is a characteristic of a two-pole rotor. Since Emax is the peak voltage or maximum voltage of the sinusoidal voltage that's induced, the RMS voltage of any phase of this three-phase stator, and I'm just going to pick the A phase for now, the magnitude of the A phase in RMS terms is equal to 2 pi divided by the root of 2 NC phi f, which simplifies to EA is equal to root 2 pi NC phi f, where f is in cycles per second of the magnetic field. Let's remove the rotor from our diagram momentarily. It's still there, it's just that I want to concentrate on the stator windings for the moment. The RMS voltage at the terminals of this machine will depend on whether the stator is connected Y or delta. If the machine is Y connected, the generator coils will be connected and will look like this. The connections are brought out to the machine terminals, which in a real-life example would look something like this, and ignore the color coding for now. This is just an example of what a terminal box for a generator might look like. Notice that the connections form a neutral, which create phase voltages EA, EB, and EC. Now this is a good example of something that you're going to have to get used to. Engineers and technologists take the liberty of designating phase voltage values without mentioning the neutral designations. So you will find, as in this example, instead of listing the voltages as E subscript AN, EBN, or ECN, they just list them as EA, EB, and EC. Then the terminal voltages include the phase-to-phase voltages, which are related by these equations. The phase-to-phase voltages are equal to √3 times the phase voltages. This is also known as the phase relationship of a balanced system. If the machine is delta connected, the generator phase coils would be connected like this. The connections are brought out to the machine terminal, which in a real-life example would look something like this. And again, ignore the color coding. Notice at this time there is no neutral, so there is only phase-to-phase voltages. And the voltages of the coils, the A, B, and C coils, are equal to the phase-to-phase voltages EAB, EBC, and ECA. In other words, the terminal voltages only include phase-to-phase voltages, which are equal to the coil voltages of the machine. Let's do a simple example problem using our simple two-pole generator running at 3600 RPM. The peak flux density of the rotor's magnetic field is given as 0.2 Tesla, and the mechanical rate of rotation of the shaft is 3600 revolutions per minute. The stator diameter of the machine is 0.5 or half a meter, and the coil length is 0.3 meters with 15 turns per coil. And we will assume that the machine is Y connected. What we want to find is what are the three-phase voltages of the generator as a function of time. What is the RMS phase voltage of this generator? And what is the RMS terminal voltage of this generator? The flux in the machine is given by 2 times the radius of the rotor times LB, which is equal to the diameter of the rotor times LB. As I said, where D is the diameter, L is the length of the coil. Therefore, the flux in the machine is going to be given by 0.5 times 0.3 times 0.2, which is equal to 0.03 Webers. The speed of the rotor is given by omega, which is equal to 3600 RPM times 2 pi radians, all divided by 60 to convert the minutes to seconds, which would equal 377 radians per second. The magnitudes of the peak phase voltages are given by Emax is equal to NC phi P, where that's the number of poles. There's 2 omega, and there will be more on this pole count later. And that's equal to 15 turns times 0.03 Webers times 377, which is equal to 169.7 volts. And the 3-phase voltages are going to be, the A phase is 170 cos omega t, B phase is 170 cos omega t minus 120 degrees, and EC is equal to 170 cos omega t minus 240 degrees. The RMS phase voltage of this generator is going to be Emax divided by the root of 2, which is 169.7 divided by the root of 2, which equals 120 volts. And what is the RMS terminal voltage of this generator? The voltage VT, or terminal voltage, is root 3 times the A phase coil. Because it's Y connected, VT is going to be equal to the root 3 of EA, the coil voltage, which is root 3 times 120, or 208 volts. We're now going to have a closer look at the internal generated voltages of a synchronous generator. Let's examine this synchronous generator now with a salient 2-pole rotor. If the rotor is turning with a speed of F cycles per second, each of the coils will generate an AC RMS voltage of equal magnitude, root 2 times pi NC phi F, oscillating with a frequency of F cycles per second. Let's unclutter the diagram now by removing the coil coloring, and I'm going to replace the flux lines with a set of flux phasors or vectors that would be appearing in the air gap. You can see that the flux lines vary sinusoidally over the face of the pole of the rotor. Remember, these flux lines would go around the perimeter of the stator and return through a primed coil into the rotor south pole. Now I'm going to replace the 2-pole rotor with an 8-pole rotor. These rotors are constructed in such a manner that the same DC current flows through each of the coils that are wound on the pole faces of the rotor. The windings are wound in such a manner as to create an alternate north and south pole on each of the pole faces of the rotor. We are interested in only the flux in the air gap, so I'm going to remove the inside polarity designation just for clarity. It's still there, it's just that I've removed them for ease of analysis. I'm going to further simplify our machine by removing the stator. In reality, it's still there. I'm just taking it out of the picture now so we can more clearly see what is happening with respect to the rotor. You'll recall when we were looking at the air gap in a machine, the flux density varied sinusoidally along the air gap over the faces of the poles. The north pole will have flux emanating into the air gap of the coil, and the south pole will have flux returning from the air gap into the pole with one complete cycle of the flux wave. This, of course, takes place all around the rotor. As the rotor completes one cycle, you can see that the induced voltage in the stator coils will go through more than one cycle. In fact, it goes through half the number of cycles as there are poles on the rotor. In this case, an 8-pole rotor, the stator coil will complete 1, 2, 3, and 4 cycles for every cycle of rotation of the rotor itself. So for this 8-pole machine, if the speed of the rotor were F cycles per second, then the frequency of the induced voltages would be 4 times that, or 4 times F. So you can easily extrapolate to any rotor with a pole count of P. The frequency of the induced voltages would be P all over 2 times F, where F is the rotor speed in cycles per second. In other words, the frequency of the induced voltage, or the output voltage of the generator, is equal to the number of poles of the rotor divided by 2 times the rotor speed in cycles per second. Rotor speeds are not usually stated in cycles per second, of course, but they're rather stated in RPM, or revolutions per minute. So in order to convert the rotor speed in RPM to CPS, it would be, to be able to use our equation then, we would divide by 60. Simplifying the equation, we get a frequency of the induced voltage, or the output voltage of the generator, is equal to the number of poles of the rotor divided by 120 times the rotor speed in RPM. So far, we have examined a synchronous generator not connected to a load, which generates terminal voltages only on the stator with no stator current flowing. If a load is attached to the terminals of the generator, a current will flow, but a 3-phase stator current flow will produce a magnetic field of its own in the machine. This stator magnetic field distorts the original rotor magnetic field, changing the resulting phase voltage. This effect is called armature reaction because the armature, or stator current, affects the magnetic field which produces it in the first place. This slide shows a 2-pole rotor spinning inside a 3-phase stator. Presently, let's assume that there is no load connected to the stator. The rotor magnetic field, we'll call it BR, produces an internal generated voltage, EA, whose peak coincides with the direction of BR. The voltage will be positive out of the conductor at the top of the page, and negative into the conductor at the bottom. With no load on the generator, there is no armature current flowing in and EA will be equal to the terminal phase voltage V, we'll call it subscript phi. Now suppose the generator is conducting a lagging load, or it's connected to a lagging load. Because the load is lagging, the peak current will occur at an angle behind the peak voltage. The current flowing in the stator winding produces a magnetic field of its own. This stator magnetic field, we will call it B stat, and its direction is given by the right-hand rule to be as shown. The stator magnetic field B stat produces a voltage of its own in the stator, and this voltage we will call it E stat. With two voltages present in the stator windings, the total voltage in the phase A is just the sum of the internal generated voltage EA and the armature reaction voltage E stat, or V phi is equal to EA plus E stat. The net magnetic field B net is just the sum of the rotor and the stator magnetic fields. Since the angles of EA and BR are the same as the angles of E stat and B stat are the same, the resulting magnetic field B net will coincide with the voltage V subscript phi. This resulting voltage and currents are shown on the diagram. The angle between BR and B net is known as the internal angle or torque angle, delta. This angle is proportional to the amount of power being supplied by the generator, and we'll see this a little bit later. Note that the voltage E stat lies at an angle of 90 degrees behind the plane of the maximum current IA. Also note that the voltage E stat is directly proportional to the current IA. And if we let X be a constant of proportionality, then the armature reaction voltage can be expressed as E stat is equal to minus JXIA. The phase circuits, the A phase in this case, is shown here, and it must satisfy Kirchhoff's voltage law, and it does because V phi is equal to EA plus E stat. Replacing E stat gives us this equation. This is exactly the same equation as the one describing the armature reaction voltage. Therefore, the armature reaction voltage can be modeled as an inductor in series with the internal generated voltage. In addition to the effects of armature reaction, the stator coils also have self-inductance and resistance. The corresponding reactance, we'll call it JXA, while the stator resistance, we'll call it RA. Then the total difference between EA and V phi, according to Kirchhoff's voltage law, is given by this equation. If we let XS represent the total internal impedance, then our equivalent circuit now will look like this. It is now possible to sketch the equivalent circuit of a three-phase synchronous generator. The full equivalent circuit of such a generator is shown here. This figure shows a DC power source supplying the rotor field circuit, which is modeled by the coil's inductance and resistance in series with RF, an adjustable resistor, or RADG, which controls the flow of field current. The rest of the equivalent circuit consists of models for each phase. Each phase, A, B, C, has an internal generated voltage with a series inductance X subscript S consisting of the sum of the armature reaction and the coil's self-inductance, and a series resistance RA. The voltages and currents of the three phases are 120 degrees apart in angle, but otherwise the three phases are identical. These three phases can be either, as we've seen before, Y connected with a line-to-line terminal voltage VT related to the line to neutral voltage by a factor of √3. Or it could be connected delta, as you see here, with VT is equal to V phase or V phi. The fact that the three phases of a synchronous generator are identical in all respects except for the phase angle normally leads us to use a per phase equivalent circuit, which is a lot more simplified. The per phase equivalent circuit of this machine is shown here. One important fact must be kept in mind when the per phase equivalent circuit is used. The three phases have the same voltages and current only when the loads attached to them are balanced. If the generator's loads are not balanced, more sophisticated techniques are required for analysis. These techniques are beyond the scope of this course. However, there are other courses that I have that will deal with asymmetrical systems. And some of these courses would include per unit analysis for single and three-phase systems, symmetrical components for three-phase power analysis, and short circuit analysis for high voltage three-phase systems. Because the voltages in a synchronous generator are AC voltages, they are usually expressed as phasors or vectors. Since phasors have both magnitude and angle, the relationship between them must be expressed by a two-dimensional plot. When the per phase voltage EA, V phi, and J XSIA and RAIA and the current IA are plotted in this way, it will show the relationship among them. The resulting plot is called a phasor diagram. For example, according to Kirchhoff's voltage law, the voltages summed around the loop must equal 0. In other words, V phi must equal EA minus JXSIA minus RAIA. A load at unity power factor, which is purely resistive across the output terminals with a voltage drop of V phi, and because it is a resistive load, it will draw a current IA, which is in phase with the terminal voltage. The voltage drop across the internal resistance is given by IA-RA, also in phase with the terminal voltage. We are now summing the voltage phasors according to Kirchhoff's voltage law. Because the internal reactance is inductive, the voltage will lead the current by 90 degrees, and it is expressed as JXSIA. Adding all the voltages together must equal the source voltage, which is given by E subscript A. The total voltage, EA, differs from the terminal voltage of phase V phi by a resistive and inductive voltage drop. All voltages and currents are referenced to V phi, which is arbitrarily assumed to be at angle 0, the reference angle. Now, let's change the load to a resistive inductive load, which is placed across the output terminals, of course, with a voltage drop of V phi. And because the resistive inductive load will draw a current IA in lagging the terminal voltage, the voltage drop across the internal resistance is given by IARA in phase with the current, which lags the terminal voltage. We now are summing the voltage phasors according to Kirchhoff's voltage law. Because the internal reactance is inductive, the voltage will lead the current by 90 degrees in this element, as expressed by JXSIA. Again, adding all the voltages together must equal the source voltage, which is given by EA. The total voltage EA differs from the terminal voltage V phi by resistive and inductive voltage drops. All voltages and currents are referenced to V phi, which is assumed to be 0 degrees. Now let's change the load, this time to a resistive capacitive load, which again is placed across the output terminals with a voltage drop of V phi. And because it is a resistive capacitive load, we'll draw a current IA leading the terminal voltage. The voltage drop across the internal resistance is given by IARA, again in phase with the current, which leads the terminal voltage. Again, we are now summing the voltage phasors according to Kirchhoff's voltage law. Because the internal reactance is capacitive, the voltage will lag the current by 90 degrees, as expressed by JXSIA. Adding all the voltages together must again equal EA. The total voltage EA differs from the terminal voltage of V phi by a resistive and capacitive voltage drops. All voltages and currents are referenced to V phi, which is arbitrarily again assumed to be at 0 degrees. These are phasor diagrams for generators operating at lagging and leading power factors. Notice that for a given phase voltage and armature current, a larger internal generated voltage EA is needed for lagging loads than leading loads. Therefore, a larger field current is needed with lagging loads to get the same terminal voltage. A synchronous generator converts mechanical power to three-phase electrical power. The source of mechanical power, the prime mover, may be a diesel engine or a steam turbine or water turbine or any similar device. Whatever the source, it must have the basic property that its speed is almost constant regardless of the power demand. If that were not so, then the resulting power system frequency would wander all over the place. Not all the mechanical power going into a synchronous generator becomes electrical power out of the machine. The difference between the input and output power represents the losses of the machine. A power flow diagram for a synchronous generator is shown here. The input mechanical power is the shaft power in the generator. The input power is the mechanical power of the shaft, and that's given by the torque times the radial speed of the rotor. The converted electrical power is given by 3 times the phase, each phase coil voltage times each phase current times the cosine of the angle between them. Once power starts to flow in the machine, you're going to have losses associated with the current flowing in the generator, which is depicted by the I squared R losses, or copper losses in the machine. The final output of the machine is given by 3 times the line to neutral voltage times the line current times the cosine of the angle between them, or it is 3 times V phi times IA times cosine of the angle between them. If we're looking at the reactive component of power, it's given by the same formula, except we're using the sine of the angle between the voltage and the current in this case. If the armature resistance RA is ignored, which it can be since XS is much greater than RA, then a very useful equation can be derived to approximate the output power of the generator. To derive this equation, let's examine this phasor diagram. It shows a simplified phasor diagram of a generator with the stator resistance ignored. Notice the 2 right angle triangles have proportional sides because they contain the same angles. That means that angle ACB is equal to the power factor angle theta. This means the magnitude of the vertical segment can be expressed as either EA sine Z or XS IA cos theta. Which means that these 2 values are equal, so they can be put into an equation. And it can be rewritten to this equation, all equated to IA cos theta. And we saw earlier that the output power is equal to 3 times V phi IA cos theta. So we can replace IA cos theta with EA sine Z all over XS. Since the resistances are assumed to be 0, there are no electrical losses in this generator, and this equation is both the P conv and the P out. This equation shows that the power produced by a synchronous generator depends on the angle Z between V phi and EA. The angle Z is known as the internal angle or the torque angle of the machine. The maximum power indicated by this equation is called the static stability limit of the generator. This happens when Z is equal to 90 degrees, which means sine Z is equal to 1, and P max is equal to 3 V phi times EA all over XS. To understand the operating characteristics of a synchronous generator operating alone, let's examine a generator supplying a resistive inductive load. What happens when we increase the load of the generator? Now we're still going to assume the internal resistance of this generator is negligible. An increase in the load is an increase in real and or reactive power drawn from the generator. Such a load increases the load current drawn from the generator. Because the field resistor has not been changed, the field current is constant, and therefore the flux phi is constant. Since the prime mover also keeps constant with speed omega, the magnitude of the internal generated voltage, EA, is going to be equal to some constant that varies with phi and omega. If EA is constant, just what does vary with the changing load? The way to find out this is to construct a phasor diagram showing an increase in the load, keeping the constants on the generator in mind. First, let's examine this generator operating at a lagging power factor. If more load is added at the same power factor, then the magnitude, IA, increases but remains at the same angle. Therefore, the armature reaction voltage, XSIA, is larger than before, but it also is at the same angle. Now, since EA is equal to V phi plus JXSIA, Kirchhoff's voltage law, JXSIA must stretch between V phi and an angle at 0 degrees and EA, which is constrained to be the same magnitude as before the load increase. If these constraints are plotted on a phasor diagram, there is only one and only one point at which the armature reaction voltage can be parallel to the original position while increasing in size. The resulting plot is shown here. If the constraints are observed, then it is seen that as the load increases, the voltage V phi decreases rather sharply, as we see here, compared to the original load before the increase. And EA has remained constrained as far as its magnitude is concerned. Now, suppose a generator is loaded with unity power factor loads. What happens if the new loads are added at the same power factor? With the same constraints as before, it can be seen that this time V phi decreases only slightly. Now suppose the generator is loaded with leading power factor loads, capacitive type loads. What happens if the new loads are added at the same power factor? If the generator is loaded with leading power factor loads, new loads are added at the same power factor. This time, IA would increase in magnitude, and having the same power factor would be at the same angle. The voltage drop across the internal impedance, which we've assumed to be XS, its magnitude will also increase at the same angle as it did before the increase. JXSIA again must stretch between V phi and EA, which is constrained to be the same magnitude as before the load increase. If these constraints are plotted on a phasor diagram, there is one and only one point at which the armature reaction voltage can be parallel to the original position while increasing in size. The resulting plot is shown here. If the constraints are observed, then it is seen that the load increases, the voltage phi increases this time, as we see here, compared to the original load before the increase. General conclusions from this discussion of synchronous generator behavior are: If lagging loads, inductive reactive power loads, are added to the generator, V phi and the terminal voltage Vt decrease significantly. If unity power factor loads, those are with no reactive power, are added to the generator, there is a slight decrease in V phi and the terminal voltage. If leading loads, capacitive reactive power loads, are added to the generator, V phi and the terminal voltage will rise. A convenient way to compare the voltage behavior of two generators is by their voltage regulation. The voltage regulation of a generator is defined by this equation, where V and L is the no-load voltage of the generator and VFL is the full load voltage of the generator. A synchronous generator operating at lagging power factor has a fairly large positive voltage regulation. A synchronous generator operating at unity power factor has a small positive voltage regulation, and a synchronous generator operating at leading power factor often has negative voltage regulation. Normally, it is desirable to keep the voltage supplied to the load constant, even though the load itself varies. How can terminal voltage variations be corrected? The obvious approach is to vary the magnitude of EA to compensate for changes in the load. Recall again that EA is equal to some constant that varies with the phi and with omega, which is the speed of the rotor. Since the frequency should not be changed in a normal system, EA must be controlled by varying the flux of the machine. For example, suppose a lagging load is added to a generator. Then the terminal voltage will fall, as was previously shown. To restore it to its previous level, decrease the field resistor RF. If RF decreases, the field current will increase. An increase in IF increases the flux, which in turn increases EA, and an increase in EA increases the phase and terminal voltages. This idea can be summarized as follows. Decreasing the field resistance in a generator increases its field current. An increase in the field current increases the flux in the machine. An increase in the flux increases the internal generated voltage EA, which is equal to K phi omega. An increase in EA increases V phi and the terminal voltage of the generator. This process can be reversed to decrease the terminal voltage. It is possible to regulate the terminal voltage of the generator through a series of load changes simply by adjusting the field current. This ends part 1 of this chapter.